Hi guys, welcome back to a new IMONST video. So in this video, we'll be talking about IMONST 1 2020, problems 14 to 17 for juniors, and then for seniors will be problems 9 to 12. So let's look at problem 14 in junior. Now, what is the smallest positive multiple of 225 that can be written using digits 0 and 1 only? Now, many people looking at 225 will be daunted because 225 is such a big number, but do not forget that 225 itself can be broken down into smaller numbers. In this case, it will become 25 times 9. So it means that this positive multiple of 225 is also at the same time a positive multiple of 25 and a multiple of 9. Now, how do we get multiples of 25 using digits 0 and 1 only? Note that you see 25, 50, 75, 100. So using this, we can have 0 zeros at the back. So any multiple of 100 is also a multiple of 25. So we can just deduce from here multiples of 100 are also multiples of 225. Now, for 9, this one's a bit tricky, but basically, if you want a number to be a multiple of 9, then its digit sum. Digit sum is a multiple of 9. Now, some of you might ask, why is this so? But there are many videos on YouTube which explain this, so I'll not explain further. Now, wait, multiple of 9. So, if we want our digit sum to be a multiple of 9 just using our 1, then we can have 9 1. So 9 times 1 will give us 9, right? So 1 1 1, 1 1 1, 1 1 1. And then later we can have, we would have 2 zeros. So because we want a multiple of 100 here, so we would have a 0 0 at the back. And after we see this indeed is, and this indeed is the smallest positive multiple of 225. You can verify this for yourself. Now, so problem 14, the answer would be 9 ones in front, and then 2 zeros at the back. So this is the answer. Okay. If you guys have any more questions, you guys can write down in the comments below. I'll try my best to answer them. So now problem 14 done. We can look at problem 15. Okay. Given positive integers a, b, and c with a plus b plus c equals to 20, determine the number of possible integer values for a plus b minus a plus b over c. Now, since we have here a plus b as the numerator, we can just consider it as one term. We can consider this as x. So we would have x plus c equals to 20. And then we would have x equals to 20 minus c. And then x being a plus b over c, we just divide both sides by c, would be x over c equals to 20 over c, 20 minus c over c, which is 20 over c minus 1. So this, if this has to be an integer, then this would imply that c is a factor. C is a factor of 20, meaning c can divide 20 into whole numbers, right? So what are the factors of 20? We just list them out. So 20 equals to 1 times 20, 20 equals to 2 times 10, 20 equals to 4 times 5. And indeed, these are the only 6. So we can try them out one by one. So we would have 20 over 1 minus 1 is 19, correct? And then we would have 20 over 2 minus 1 is 9, also correct? 20 over 4 minus 1 is 4. 20 over 5 minus 1 is 3. 20 over 10 minus 1 is 1. And then 20 over 20 minus 1 is 0. But again, look, think again. Can 20 over 20 be a term? Okay, so let us see. If we have c equals to 20, then we would have x being 0, right? So can we have two positive integers, a plus b, such that their sum is 0? Of course not. The minimum for a plus b would be 1 plus 1, which is 2. So this is smaller than 2, so this is not possible. In fact, there are only 1, 2, 3, 4, 5 legitimate values for a plus b over c. So if we want positive integers and possible integer values as the condition. So the answer to problem 15 would be 5, okay? Now, Let us continue to look at question 16. So for question 16, if we divide up 2020 by prime p, the remainder is 6. Determine the largest possible value of p. So basically, if we do long division, we can draw it out like this. 2020 divided by p is some quotient a, and then we have a p over here, will give us 6. Now, rearranging this stuff would give us 2020 equals to some multiple of p. So a is being the multiple. AP plus 6, right? Because the remainder is 6. So we can minus 6 on both sides. We will have 2014 equals to AP. Now, how do we find the maximum value of P? Now let's find. Since we know 2014 is a even number, so we see that 2014 equals to 2 times 1007. Now, is 1007 prime? We need to find it out. So what we would do is, if we want to determine if 1007 is a prime, let me teach you guys a trick. Okay, I need to demonstrate this with an example first. Let me think of one. So it would be it will be 231, right? So 231 is obviously not a prime, but okay, 247. 247, we don't really know if it's a prime, right? So you see, let's take the root of 247. So 247 root is between 16 and 15, right? So what we need to do is check all the primes. Check all the primes smaller than 16, okay? And then see if they can divide 247. If they can divide 247. Why is this so? Because every time you split up, you can see, if we take 247 here, it actually is 1 times 247 and then 13 times 19. So we know that this is not a prime number, it's a composite number. But observe that every time you split it up into two smaller numbers, one of them must be smaller than the root of 247 itself. So using the same principle, we can just take the root of 1007. So 1007 is, root 1007 is larger than 31 but smaller than 32. So what we need to do here is check all primes smaller than 32. So with all of these include 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. So you need to check them one by one and then check if 1007 is divisible by any of these. But of course, since I have done this, this process of finding if any of these primes divide 1007 is up to you guys. So you guys can pause here for 5 seconds while I continue to solve the problem. So what I found is 1007 is 19 times 53, and then we do the same process again and see if any of the primes smaller than 53 or 19 divisible by any of these. So we find that 53 in itself is also a prime. So we know that this 2014 is 2 times 19 times 53. So the largest primes out of all of these is obviously 53. So determine the largest possible value of P. P would be 53. Okay, and this is the answer to problem 16. Now, for the last question, I have two solutions. Again, like before, one is the proper one is the improper one, and I don't advise you guys to do the improper solution. Now, for problem 17, this is also quite cliche, I would say. So let's read the title. Read the question. A football is made by sewing together some black and white leather patches. The black patches are regular pentagons of the same size. The white patches are regular hexagons of the same size. Each pentagon is bordered by 5 hexagons. So we need to jot this down. Each hexagon is bordered by 3 pentagons and 3 hexagons. We need 12 pentagons to make one football. How many hexagons are needed to make one football? Now, let's look at this problem from the perspective of one white hexagon, right? Because we know that as is stated in the problem, one white hexagon is surrounded by 3 black pentagons. As we can see here, I know my drawing's a bit shitty, but anyways, so something like this. Okay, and then this one is the white hexagon, and then something like this. Okay, so this is something we need to know. Now, we know that each pentagon is bordered by 5 hexagons, right? And then we need 12 pentagons to make one football. So our initial intuition will give us, so intuition. So the number of hexagons needed. Number of hexagons needed would be 5 times 12 equals to 60. But this is way too much. Why? I'll tell you in a second. So look at now let's switch our perspective to these pentagons, sorry. So these pentagons are surrounded by another 5 hexagons, right? So something like this. Then, no, I need to color them black first. So something like this. Okay. And then this one. And then this one would be something like this. Then the last one, so this last hexagon. 1, 2, 3, 4, 5, 6. Okay, it's a bit ugly, but please don't mind. Look at this. Okay, so if we label this pentagon as 1, so you see that this hexagon is counted 1 time. No, this one we label as A. Then we label this hexagon B, and then we count its surrounding hexagons. This is counted twice. And then this is pentagon C. Then we see that this hexagon is counted thrice. So this happens, the same thing happens to all of the hexagons on this football. So we see that each hexagon is counted thrice. So we need to write this down. Each hexagon counted thrice. So what we need to do is to divide 60 by 3, and then we will get our answer, which is 20. So our answer for problem 17 is 20. But now, our video has not ended yet. We have another solution, right? Okay. So our second solution is to find Google and then just find how many hexagons are there in a football, and then it'll just give you the answer. As you can see, 20 hexagons. It is the same as what we've done, but the lesser the effort, the better. I don't know. Okay, don't follow this, please. Okay, if you like my video, please give a thumbs up, or you could show some support by subscribing, because I would occasionally put out some math content, just solving some past papers. Now, this is the end of the video, and then in the next video we'll be talking about problems 18 to 20 junior, and then problems 13 to 15 senior, which are the same thing. So ciao ciao.